Welcome to this explainer. Today, we're exploring the absolutely magnificent Caldwell 43, or as it's better known, the Little Sombrero Galaxy. If you're a fan of cosmic architecture, you are going to love this. We're not just going to admire the pretty, glowing center you usually see in amateur astrophotos. Oh no, we're using cutting-edge space telescope data to peel back the layers, uncover a pretty violent history, and trace the vast, invisible boundaries of this distant island universe. Here's how we're breaking it down today. First, we'll meet the Little Sombrero. Then, we'll dissect the galaxy layer by layer, explore its extended stellar halo, and finally, decode the secrets hidden in its colors. All right, let's get into it. Section 1. Meet the Little Sombrero, a distant marvel.
So, located about 40 million light-years away from us in the Pegasus constellation, Caldwell 43, officially cataloged as NGC 7814, is what we call an SAB-type spiral galaxy. Basically, that just means it's sporting a very prominent, tightly wound central bulge right alongside a distinct disk. But here's the catch. Because of how it's oriented relative to Earth, we don't actually see those classic swirling spiral arms you probably picture when you think of a galaxy. Instead, we get a view that's arguably way more revealing.
We are viewing this galaxy almost perfectly edge-on. Sitting at an inclination of roughly 90 degrees, the Little Sombrero is totally sideways from our vantage point. And honestly, this is a huge advantage. It lets us see the galaxy's vertical anatomy without all the blinding light of a face-on disk getting in the way. We can clearly see the tightly packed gas and dust along the galactic plane and contrast it with that massive glowing bulge pushing out above and below it. It is literally the ultimate profile shot.
Moving on to Section 2, Dissecting the Galaxy, a Cosmic Anatomy Lesson.
If we really want to understand how a galaxy is put together, we have to look past what our eyes can see. That's where Spitzer's 3.6-micron photometry comes in. Spitzer observes in the infrared, which is like having cosmic X-ray vision. It cuts right through the obscuring dust and highlights the older, heavier stars that hold most of the galaxy's mass. The data here is wild. The Little Sombrero's thin disk is incredibly flat, with a scale height of just 0.44 kiloparsecs. That's less than 1,500 light-years thick. Now contrast that paper-thin disk with the central bulge, which just totally dominates the inner region. That bulge is shining with the luminosity of 70 billion suns, 70 billion.
And you can see that stark contrast perfectly mapped out right here. This shows the radial light distribution of NGC 7814. Basically, it tracks how light intensity changes as you move outward along the plane of the galaxy. See that intense, sharp peak right in the center? That's our massive bulge. Then look at how it drops off into a steady, predictable slope as we move out along the thin disk. It shows that once you escape the chaotic, crowded center, the disk is actually incredibly mathematically ordered. But here's the thing, that disk, it's really only a tiny fraction of the galaxy's true footprint.
Which brings us to Section 3, the extended stellar halo, beyond the disk. This is where our explainer shifts from the obvious stuff into the invisible. What actually lies beyond that glowing disk? If we look way out to projected distances of 50 to 70 kiloparsecs from the center, we're talking roughly 160,000 to over 220,000 light-years out. What's hiding there? Remember how tightly constrained that main visible disk is? Well, if we look tens of thousands of light-years past the edge of that disk, out into the deep, dark void, is it really just empty space?
The short answer? No, it is definitely not empty. Enter the stellar halo. Now, every massive galaxy sits inside a huge envelope of dark matter. But there's also a stellar halo, this faint, ghost-like sphere of ancient stars scattered way out in the outskirts. These stars are incredibly sparse and super faint, which makes them notoriously difficult to detect. You can't just snap a quick picture. You need some serious, long-exposure heavy lifting from space telescopes to pick them out from the cosmic background noise.
And that heavy lifting was done by the GHOSTS survey. Using the Advanced Camera for Surveys and the Wide Field Camera 3 on the Hubble Space Telescope, astronomers peered deep into the dark outskirts of the Little Sombrero. They weren't just picking up a blurry glow either. They actually resolved individual ancient red giant stars out to 50 to 70 kiloparsecs. Think about that scale for a second. The galaxy's visible disk has a scale length of just 4 kiloparsecs. Finding stars 70 kiloparsecs out proves that the visual boundaries of a galaxy are kind of an illusion. The Little Sombrero is vastly larger than it appears in your standard telescope.
Section 4, Secrets in the Colors, the Fossil Record.
Okay, this is the real detective story part of our explainer. Why go to all the trouble of hunting down these faint, lonely stars so far from home? Because their light holds the history of how the galaxy was actually built. Check out the bottom right panel here for NGC 7814. In astronomy, an ancient star's color is a direct fingerprint of its chemical makeup. The GHOST survey plotted the colors of these red giants as they move further from the galactic center. If you trace those blue dots for NGC 7814, you'll see a clear trend. As you move right on the x-axis, meaning further into the galaxy's outskirts, the median color of the stars drops. It trends downward.
So what does a downward or negative color gradient actually mean? It directly translates to declining metallicity. Basically, the further out you go, the fewer heavy elements these stars have. And this logic is absolutely profound. You see, older, smaller dwarf galaxies are generally metal poor. They just haven't cooked up a lot of heavy elements yet, which makes their stars look bluer through these specific Hubble filters. Because the little Sombrero's halo gets progressively more metal poor the further out you go, it tells us exactly how this halo came to be. It didn't just form all at once from one giant gas cloud. Instead, it was stochastically or randomly assembled. Over billions of years, the little Sombrero's immense gravity just continuously pulled in, tore apart, and absorbed smaller, metal-poor dwarf galaxies.
Put simply, this halo isn't just a random cloud of stars. It's a cosmic fossil record. It is quite literally made up of the digested remnants of smaller galaxies that Caldwell 43 consumed to fuel its own growth. Every single one of those faint red giant stars drifting 50 kiloparsecs out in the dark, that's a surviving relic of a completely different galaxy that happened to wander a bit too close eons ago. By mapping these stars, we're not just measuring distance, we are doing galactic archaeology, unearthing billions of years of violent history from the shadows.
We started this explainer looking at the little Sombrero galaxy simply as a beautiful, edge-on disk sitting 40 million light-years away in Pegasus. But once we peered past the obvious, using infrared and deep Hubble optical data, we uncovered a sprawling graveyard of absorbed dwarf galaxies stretching hundreds of thousands of light-years into the void. It is a staggering thought. When we look up at the night sky, we have to ask ourselves, how much of the universe's history are we completely missing just because it's too faint to see? Thanks for joining me on this explainer. Keep looking up and remember to always look closer.